So far we have proved the local central limit theorem from DeMoivre-Laplace. We are going to do now the global form, which talks about distribution functions and ranges of random variables, as opposed to the local form, which talked about mass functions and density values. So you can hopefully feel the meaning of the words local and global. It will also be apparent that the global form of a central limit theorem is weaker than the local form. So we are going to deduce the global one from local. And this global version, as you'll see, will probably be familiar from earlier probability studies of yours. Here is what we did in the previous videos. We proved the DeMoivre-Laplace central limit theorem. And actually this is called a local form. It's going to be local because we compare the mass function with the density of normals. Okay, the standard normal density is phi. So we compare the mass function, which is a local quantity, with the density of normal, which is a local quantity again, and that's why it's called the local theorem. In this video I'm going to show you about the global theorem. And one more remark which I want to emphasize from the proof is that we prove that the mass function is close to this kind of transform of the standard normal density, except that we still don't know this constant pi hat, whether it's the same as pi. So in fact what we proved is that the mass function is close to a version of phi with some other constant pi hat here. Okay, so we almost proved the local theorem, except that in phi we are actually using some kind of a different constant pi hat. And in this video, we'll finally solve the mystery whether pi hat is pi. Of course it is. So, let me state the theorem. Let P be fixed again, and X be a binomial NP, random variable. So the same conditions as before. Then, for any A smaller than B reals, we have that the probability of the binomial random variable standardized, so subtract the mean divided by standard deviation, Q is again 1 minus P, of course. The probability that this is between B and A converges as n goes to infinity to phi of B minus phi of A, where phi is the standard normal distribution function, the integral of little phi. And this is a theorem which should be familiar from probability 1. So towards the end of probability 1, maybe the middle of probability 1, the normal approximation of binomial is covered. That's the same theorem. So let's prove it based on the local theorem, and this proof will also show you in general there is nothing really specific about central limit theorems, about normals. This shows you that the local limit theorem is always stronger than a global one, because the local limit theorem will just imply this global statement. Okay, so let's do the proof based on the local central limit theorem. So what do we want to do? We want to look at this probability and this difference of phi's and show that they are close. So we're going to look at the probability that x minus np over root npq between a and b. We look at this probability and we compare it with phi of b minus phi of a, and we want to show that the difference is small. So what is this difference? First of all, if I want to solve this inequality for x, then I find that x is bounded from above by, let's solve it quickly, b of square root of npq, b of square root of npq plus np, and from below by a of square root of npq plus np. That's where the range of x is according to this event. So what's the probability of that? Now the probability of that for a discrete random variable, for x is actually an integer random variable, the probability of that is summing up the mass function on this range. So that's what I'm going to do exactly. So this is the probability is going to be the sum from a of square root of npq plus np to b of square root of npq plus np, except that there is a little problem here. A of square root of npq plus np is not necessarily an integer. In fact, in many cases it's not, and also the upper limit is not necessarily an integer. So the integer k has to be in between these two bounds, and therefore if I just put an upper integer part here, then the thing starts to make sense. And if I put an upper integer part there, then again it makes sense, because x is between, or k is between these two bounds if and only if it's between the upper integer. Well, actually this is generous. For the upper integer part is generous. So I'm just going to add here smaller than or equal, because I extend this range a little bit. When this is not an integer, I think I'm adding 1 here. It doesn't really matter. And anyway, this now makes sense. This now makes sense because k is from an integer to another integer, and that's bounding from above this range. And so on that range, I need to sum the mass function. Okay, and this part here is the distribution function of standard normal. Phi of b is the integral from minus infinity to b of the standard normal density. Phi of a is the integral from minus infinity to a. Together, this difference will be the integral from a to b of the density of standard normal. Okay, so this is what I can write for that difference. And now comes the triangle inequality. I'm going to insert my approximation from the local theorem. So I'm going to write out again the sum, the exact same thing as before, to b root npq. So again, these are the upper integer parts of this potentially non-integer number, pxk. And what I'm going to do here is I'm going to subtract, still under the sum, I'm going to subtract 1 over square root of npq, and then phi of k minus np over square root of npq. So now obviously this is a different term from before. And what I'm doing here is I subtract this term, but I'm going to add it back in the next line. So I'm going to have the same sum. Let me not write out the limits. It's the same limits, right? So upper integer part of a square root npq plus np to upper integer part of b square root npq plus np. Same limits. And then I'm going to add back whatever I subtracted here, npq under the square root, and phi of k minus np over npq square root. And so that's now added back, so I cancelled it out, except that I went with the triangle inequality underneath with the absolute values, and then I still have the integral from a to b phi of x dx. Okay, so what happened here is I added this term in together with this sum. I subtracted that term, I subtracted first and added second, and otherwise the mass function and the integral stays. And then I went underneath the sums and subtractions with the triangle inequality. So I brought the two absolute values separately for these two terms. Okay, now I'm going to start with the second term, because I'm going to say that what I see here is exactly a Riemann sum. It's exactly a Riemann sum. I'm going to call x as k minus np over root npq. So dx, as k goes through integers, and k is my summation index, so I need to look at what k does. K goes through integers, then dx is going to be 1 over npq under the root. This is how much x changes every time I increase k by 1. And this of course goes to 0 as n goes to infinity. So I'm actually doing a finer and finer summation of phi of x times dx. So this is going to be my dx term. This is going to be my dx term. All of this. And this is going to be phi of x. So phi of x is here. Dx, an approximation of dx, and the approximation of phi of x together with the sum. This is a Riemann sum. Okay? So that's why the second term, this second term here, converges to 0 as n goes to infinity, because that integral is exactly approximated by this Riemann sum. The boundaries also match up. Notice that the boundaries also match up. When k is a square root of npq plus np, then k minus np over root npq is approximately a. There is a small 1 over root n order error because of the integer part, but that of course goes to 0 in the limit. And when k is b square root of npq plus np, then k minus np over square root of npq is b, plus a little error caused by this integer part, which is divided by npq root, so that the error vanishes in the limit. So the second term goes to 0. Okay? This leaves us with the first term. So the claim, of course, is that the first term also goes to 0, and that's, of course, where the local central limit theorem comes in the picture. Okay, so the first term is the difference between the mass function and 1 over root npq phi of k minus np. And that's exactly what the local central limit theorem told us about. Phi is a bounded function, right? It's the bell curve, it's bounded. So I can actually move phi over to here. I can divide by 1 over square root of npq, which is small. And therefore I need to show you some transformations which justify that I can use this form of the local central limit theorem. So for the first term, I'm going to do a couple of more steps. I'm going to look at the maximum of pxk minus 1 over square root npq and phi of k minus np over root npq. And the maximum will run for k minus np mod smaller than some constant times root n. So why am I doing this? Because this difference is exactly what we see there. And notice that k is np plus something in the order of root n. Or minus, I mean, it's around np plus minus something in the order of root n. Okay? So that's why I'm going to do this maximum here. I want to find out the largest possible difference between my two terms in the range when k goes through the range of the summation. And that's equivalently written with some constant, which is something like a or b times square root of npq. This constant times root n is bounding k minus np, because k is np plus that and np plus the other. Okay? So if I can show that this is small, that will help me in doing that summation. Okay, so let's see what this is. This is the maximum of over the same range, k minus np smaller than c root n. And then I'm going to divide p of x k. I'm going to add here square root of npq, and I'm going to divide by phi of k minus np over root npq. I'm going to subtract 1 here, and now of course the two sides are not equal because there is a factor difference between them. What actually happened is that I multiplied both the first and the second term by the square root, so I have to divide by the square root. And I also divided by phi both the right hand side and the left hand side, so I have to multiply back with phi. Okay. And so now I can do two things. The first thing I'm going to do is that I'm going to bound this by the error term I get from DeMoivre-Laplace on the first term. So the first term is now really in the same form. The first term is now really in the same form as DeMoivre-Laplace, the local DeMoivre-Laplace, because I have the mass function square root npq over phi minus 1. That's in the same form. And notice that an is the constant c. So the range is also on the same form, except that an is just the constant c. So I'm going to just use an as a constant, which is absolutely fine, because it's non-decreasing and dividing by n to the 1/6 goes to 0. And so the first term, the first part of this by DeMoivre-Laplace CRT is big O of an cubed, which is c cubed, over square root of n. That's the first term. Okay? The second term is phi at some number here. And what is phi? Well, phi is 1 over root 2 pi, except I don't really know what this constant is, so I'm going to use pi hat. And exponential of minus k minus np square over npq and the 2. That's what phi is. The main point here is that there is this constant here and there is an exponential of a negative number, so this phi is in the order of 1. So really what we're having here is some constant over square root of n from here. The constant includes the 1 over root 2 pi hat, it includes p and q, and it includes a 1 for the exponential. And so together this is in the order of 1 over n. And at this moment we are done. We are almost done, because what we showed here is that each of our summands in the first term, each of our summands is in the order of 1 over root n. But we have many of these terms, so we have to be still a little bit careful. How many of these terms do we have in that summation? So when we do this sum, from square root of integer part of a, square root of npq plus np, upper integer part 2, upper integer part of b, and square root of npq plus np, upper integer part. When we do this summation, which we had up here, when we do this summation, then we have, this sum has, in the order of, b minus a times square root of npq times square root of n. So in the order of square root of n many terms. They are uniformly bounded by big O of 1 over n. This bound here is uniform. I could take a maximum in the local theorem, so I don't depend, my bound doesn't depend on k anymore. Uniformly bounded, so these are uniformly bounded, and they are uniformly in the order of 1 over n from the previous slide. So combined, my first line here summing all of these differences in that range combined is bounded, or is in the order of square root of n times 1 over n, so 1 over root n. and this thing goes to 0 as n goes to infinity. So at this moment I'm done, because I proved that the difference between the probability and the approximating distribution function difference is bounded by two terms, this sum here and the Riemann sum minus the integral there. The Riemann sum minus the integral goes to 0 by definition of integrals. And this sum here, I looked at the maximal distance between the maximal value of the summands, uniformly bounded by 1 over n, and I have square root of n many terms to sum up. So together it's order 1 over square root of n goes to 0. So I'm done at this moment. Okay. Except that I still don't know about the constant in phi. So what we proved is that the probability that, so what we have is that the probability of x minus np over square root of npq being between a and b is converging as n goes to infinity to phi of b minus phi of a, or if you want integral from a to b of phi hat, which is 1 over root 2 pi hat. We still don't know about this constant, e to the minus x squared over 2. This is what we proved. But we still don't know the constant. However, now let's take a goes to minus infinity, b goes to plus infinity, then this probability goes to 1. The right hand side has to go to 1 as well. And we know that it will only go to 1, so left hand side converges to 1, so therefore the right hand side needs to converge to 1 as well, as a and b goes to infinity. Okay? And this only happens if pi hat is actually pi, because we know that the integral of 1 over root 2 pi e to the minus x squared over 2 is 1, and if we change pi to some other constant, then it's not 1 anymore. Okay, so that is the moment when, using probability, we can conclude that the constant pi hat, which we are actually carrying over since Stirling's formula, the constant pi hat is indeed pi. That is the moment from the global theorem where we can conclude that. And so now we prove the Stirling formula with the constant pi, we prove the local central limit theorem, the local DeMoivre-Laplace central limit theorem with the constant pi, and now the global central limit theorem, this one, with the constant pi. So now everything is complete, and we have both the local and the global CLT for binomial random variables. Much later on in this unit, we are going to the full central limit theorem for independent sums, and of course the binomial is in distribution an independent sum of Bernoulli's. So with completely different methods, the full central limit theorem is containing at least the global, the version we prove will contain the global DeMoivre-Laplace theorem, not the local one. But still, this was done much earlier in history, and I think it's quite a nice limit theorem and quite a down-to-earth, bit complicated, but still down-to-earth calculation, which is worth looking through.